So we're going to start discussing another inferential test technique called the ANOVA, or analysis of a variance. So that's ANOVA. So it's usually listed as all capitals ANOVA. However, it represents analysis of variance. But before we do that, just briefly, I wanted to summarize the t-test for independent and dependent samples. So again, just kind of comparing and contrasting these two, the t-test for independent groups, an inferential test for two group between subject designs, to where when we have an IV with two levels, two different groups of people that are different people, they're independent or they're between each other, and we have a single outcome, which is a continuous variable. It checks for systematic differences between the groups on performance, some form of DV. Again, some of the assumptions are a categorical IV with two levels, interval or ratio dependent variable, bell-shaped distribution of that dependent variable, and a homogeneity and variance when we compare what the variance looks like, not the midpoint, but the distributions of those two different groups. And a major, excuse me, a major assumption is the independence of observation. This is usually just handled by the research design itself, but it is important to remember that if you have everything going for you, you have two groups, they're different people. However, the first group is allowed to communicate with the second group in such a way that it might influence their outcome. You no longer have independent observations. We also discussed the t-test for dependent groups, also called a within subjects design. In this case, it's almost identical. We still have an IV that's two levels. We still have a DV, which is ratio or interval. However, the difference here is that the same people or a matched set of people are the actual people that are in both groups. So it checks for systematic differences and individual difference within the groups. In other words, how does the group itself change from condition 1 to condition 2? And we discussed some of the potential limitations with this, especially order effects. Again, we have a categorical IV with two levels. We have an interval or ratio dependent variable. We need that bell-shaped distribution, and we still need that homogeneity of variance. The difference here is that the observations are by their very nature going to be dependent on each other, which is one of the reasons for that test name being dependent groups in addition to the within subjects design. So again, just two different ways to refer to it. Independent tests can also be called between groups. Dependent tests can also be called within groups. Now, we can do a lot with t-tests, and in fact, a lot of early science did, but what we are missing here is the ability to be more complex. We can only look at a single dependent variable, and we can only have an independent variable which has two levels. The analysis of variance is going to slowly open those doors for most of the other types of more complex designs we'd be interested in. So again, just thinking through what we've been added in this class, the first question we ask is how many variables. If there's only one, we have a t-test or z-test for independent samples. If we have two variables, the question becomes, is the categorical IV how many levels? If the categorical IV is continuous, we're at regression or correlation. If it is a 2, we then ask, is it a between or within subjects design? If it's a between subjects design, different people in each condition, we use the t-test for independent measures. And if it's a within subject design, the same people in each condition, we do the t-test for dependent measures. We're now going to add to that, as we actually are going to ask the question, if we have more than two variables or our categorical variable has more than two levels, what do we do? So again, if we have two or more, so basically 3 plus categorical IV, so we have a categorical IV with 3 or more levels, again, we're going to ask that between or within subjects design. And if it's between, we're going to be using the independent measures ANOVA, which is what we're going to discuss now. So ANOVA, analysis of variance between. We'll also be talking in future lectures about repeated measures, ANOVAs within, and also factorial ANOVAs. And the big difference between a regular between or within subjects ANOVA is we still have a single independent variable, and it's categorical. It just has 3 or more levels. In factorial ANOVA, we actually go to another level of complexity where we have more than one independent variable. We have multiple independent variables that we're looking at. But we'll reserve that for a later lecture. So again, t-tests are used to analyze the difference between two groups. It's expressed as sample means. If we're comparing 3 or more groups, we could use t-tests. Does a t-test allow us to make this comparison? Not a single t-test. And we would have to run multiple t-tests. We'd have to run a t-test between group 1 and group 2. We'd have to run a t-test between group 1 and group 3. And we'd have to run a t-test between group 2 and group 3. So we'd have to run multiple tests in order to make this comparison. And before the analysis of variance, this might very well be what needed to be done. However, the problem here is that if we are doing multiple tests, we're increasing the chance of us making an error. And this is just pure, simple probability. Our probability measure is dependent on the test being in isolation. In other words, when we calculate whether or not a test is statistically significant, it is unaware of any additional tests. It's assuming it's the only test we are doing. So if we claim that we ran a single t-test and that we found a significance of below 0.05, we are fairly confident that that's what it means. However, if we in reality know we actually ran two t-tests on the same data, in other words, we compared group 1 and 2 and we compared group 2 and 3, then the chance that one of those two tests is actually insignificant, even if both were p of 0.05, it's actually 9%. And likewise, if we actually looked at three levels completely, three tests, 1 to 2, 2 to 3, and 3 to 4, at that point, we actually have a 14% chance we're wrong. So one of the problems with running a simpler test multiple times the same data is we start to get a warped view of whether or not we actually are correct. So we need a test that can be actually looking at group 1, 2, and 3 in a single analysis so that our significance value is also meaningful. So that's where the analysis of variance comes in. It allows us to compare more than two groups at a time, and it adjusts for these multiple comparisons. It's an omnibus test for statistical probability. And that is going to be a concept we're going to run into within this class. So all the ANOVAs we're going to discuss are omnibus tests. But also, if you continue down this road of additional statistical techniques, most advanced statistics are, at least initially, an omnibus test. What an omnibus test means is that the initial test is simply asking, is there significant differences throughout my model? So if I have three groups looking at a single DV, the omnibus test asks the question, as far as statistical significance, is there some difference in there that is meaningful? If there is, the omnibus test is significant, we're actually not done. That means we now have been given license to see where the differences are. So the initial omnibus test of the ANOVA doesn't actually necessarily tell us, does group 1 differ from group 2? Does group 2 differ from group 3? Does group 1 differ from group 3? And vice versa. What it tells us is there's a difference that is statistically significant somewhere. So we're going to focus on three types of ANOVA in this class, and we're going to start with the independent measures between subjects ANOVA, which is the subject of this lecture. The analysis of variance measures variability between the measure and attempts to account for that source of variance. So again, there's two types of variance here. There's between groups variance, variance that measures the difference between group means, and that's going to be on the top of the equation. So we're looking, is there a meaningful difference in some form between our various conditions? And the within group variance, variance that measures the differences within each group. Sometimes error, variance, noise, and confound, and this is generally going to be at the bottom of our equation. So again, even though ANOVA is getting a lot more complex as far as how we calculate one, it is still looking at the same concept as t-tests and even t-tests for single samples. All of our variances, all of our analyses, all of our inferential statistics basically are putting the actual differences between conditions at the top and overall variance at the bottom. And if that difference between the actual intervention, if you will, or variable of interest, or IV, is big enough that it actually eclipses the overall variance, that's when we can start talking about it being statistically significant. So in conducting a hypothesis test, we're looking for a between groups difference. We're looking for basically there's a difference between our treatment or treatments and when those treatments are not there, often referred to as control. We must account for any differences among people within the groups. So within group variance acts as a source of error. To maximize the treatment effect and reduce error, it is best to be consistent that the measures are given to all subjects, be consistent the treatments given to all subjects in the same group, and also using random assignment to try to get rid of or at least randomize the differences between our groups. This will generally work, but is still one of the reasons we test for that homogeneity variance to find out, did it work? So the analysis of variance allows us to compare more than two groups at one time. It basically allows us to do multiple t-tests without inflating our type 1 error rate. As I said, there's several types of ANOVA, the between subjects, within subjects, and factorial, and we're going to cover all of these, but we're mainly focused on the between subjects now. So the properties of a one-way ANOVA, and one way is just another way to say it's not a factorial ANOVA. There's a single independent variable. We have an outcome that is still continuous, so we still have that same requirement from the t-test. The dependent variable, our outcome, is still only a single variable. And our predictor is a variable that is categorical with 3 or more levels. There is no limit to the number of categories, commonly known as conditions or groups or factors. But however, adding additional conditions decreases the degrees of freedom, making it less likely we'll find an effect. So you can have a one-way ANOVA with 3 categories, 4 categories, 5 categories, 6 categories. Really doesn't matter. It just becomes more complex to interpret, and it also decreases the chance of you finding a difference. The more categories we have, generally the harder it is to find. And a lot of the things we might be interested in often will fall themselves into 3 categories. For example, the example we were using for the t-test was mass study versus separated study. So in one condition, everyone studied for 6 hours straight. The other condition, people studied twice for 3 hours over a different period of time. We might ask, what happens if you don't study at all? And that would be another condition. So that would be a one-way ANOVA where we have an independent variable, mass study, separated study, and no study. And that no study would often be what we refer to as the control group to find is there really a difference across the board. Again, our DV would be test performance, which would be continuous. So I just want you to kind of recognize that there is an enormous amount of complexity in the IVs when we get to ANOVA. We can have multiple IVs, we can have multiple levels in those IVs. However, the IVs still need to be categorical, and there still needs to be only a single continuous outcome variable. Everything we've discussed in this class as far as inferential statistics, and generally most of what you discuss as an undergraduate level, are what we call univariate analysis or univariate inferential statistics. And that doesn't refer to the number of IVs. It refers, uni means one, variate, one variable. It means the outcome. If you get to more advanced statistics, especially in a lot of graduate classes, we start talking about multivariate inferential statistics. And these are even more complex techniques that have multiple independent variables, but can also have multiple outcome variables. For the most part, we're going to avoid those, but I do want to at least acknowledge that difference and acknowledge the terminology. So the logic of ANOVA. If the null hypothesis is true, the groups are equivalent on the DV across the board. The treatment effect are equal to 0. The between group variability is equivalent to the within group variability. In other words, there really is no difference in the individual group's difference compared to just the overall variance. And in this case, the calculated test statistic is going to be 1 or very close to 1. F is, again, italicized F is the acknowledgement or indication that an ANOVA was run. So when we run an ANOVA, we're reporting an F. And as far as what that number is, it's always going to be positive. It doesn't matter what the order is because of the way it's actually calculated. And it's usually going to be 1 or higher. But 1 generally means there isn't a relationship. If the alternative hypothesis is true, at least one of the group means is different from the others, and it's statistically significant. It is probable at a 95% level that effect is because of your intervention and not some random chance. The treatment did have an effect. And the expected value of F, therefore, is going to be greater than 1. And F doesn't really have a limit. We can see F's of 2, 3, 5, 15, 20. The larger the effect, the bigger the F. So just a little bit of history. The father of the ANOVA was Ronald Fisher. He was an English evolutionary biologist, a geneticist, and statistician. He lived from 1890 to 1962 and was extremely well published, 395 published articles. So ANOVA is one, and many of the subcategories of ANOVA were created by Ronald Fisher as a way to be looking at more complex statistical analysis. So the logic of ANOVA here, we have t-tests are based on the mean difference between two groups and it accounts for error. The ANOVA, the difference is determined by variance between the groups. So we're looking at total variance. Again, the initial ANOVA is actually an omnibus test. It doesn't tell us where the difference is. It simply looks at the overall picture and asks, is it likely, again, that p-value, that it's 95% likely or higher that there is an impact of the difference in the groups. Error is determined by the variation that cannot be accounted by these effects. So again, theoretically, what F is the mean squared between divided by the mean squared within. And what is mean squared between? It's the sum of squares. In other words, it's all of the differences throughout the data summed and then squared. That's why it's always a positive number, divided by a degrees of freedom. And it's divided by the sums of squares within. And that's all of the variance, again squared, divided by the degrees of freedom. And that becomes the bottom of our equation. So again, I'm not necessarily expecting you to look at this and suddenly know how to calculate this. What I'm wanting you to understand is theoretically, all inferential statistics are always looking for effect on the top, total variance on the bottom. So when to use an independent measures t-test, or ANOVA, I'm sorry. The test is used when your design meets two criteria. It compares 2+ groups. In other words, you can, by the way, run an ANOVA with only 2 groups. However, parsimony, which is the concept of always keeping things as simple as possible, why not just run a t-test at that point? So there's a simpler tool to use the simpler tool. So generally, we're going to do it with 3 or more groups of treatments, and it uses different subjects for every condition. That's why it's an independent measures. It's a between measures design. This is especially useful when you have access to larger sample sizes. You may not be able to test and retest the same people, or you're worried about possible maturation or carryover effects. So maturation means people are naturally getting better over time. So think about how your understanding of statistics have hopefully advanced during this class. If I tested your understanding of statistics at the start of the class, in the middle of the class, and the end of the class, I would expect those scores to go up regardless of any other intervention. That's maturation. Carryover effects means that if I give you the same test at time 1, time 2, and time 3, you're also going to just get familiar with the test. So by the time you're at the end, if this was a within subjects design or a repeated measures design, I'd be worried about carryover effects. You're just learning the test. However, if I gave different people the test at the start, at the middle, and the over, I'd be less worried about these effects. So we're going to talk more about the ANOVA in the next slide group as we continue to talk about how we can use this tool for various purposes.